Howdy and welcome to Primary Structure. In this video, we are going to begin with dialysis. And dialysis is used, remember, dialysis is the movement of solute from high concentration to low concentration. Dialysis is used whenever we are talking about salt. So if we salt out our protein in a fractionation step early on, as we did in a couple of videos ago, we need to remove the residual salt from our sample before we load it onto an ion exchange column where the salt would interfere with the charge of the protein interacting with the charge of the solid phase, right? We also typically elute from an ion exchange column with high salt, so we typically use dialysis again to move the salt from high concentration in our sample test tube out to the dialysis buffer outside the bag in order to reduce the amount of salt in our sample. So we remove the salt by placing our sample into a semi-permeable bag. It's very similar to a sausage casing. And we can buy these with different pore sizes. And so depending on the size of your molecule, you would want to pick, of course, a pore size smaller than your favorite protein, your insulin, for example, but large enough to let the salt or whatever other materials you want to dialyze out. Okay, add a sample bar and a mixing plate, and your dialysate is your low salt buffer, which is going to cause the solutes, the salts, to move down their concentration gradient from high concentration inside the bag with your protein to out into the dialysate where there is low salt. And we do this for a couple of hours, and we change it a couple of times, and then we're ready to move on to our next step in our purification. And that next step may be gel filtration chromatography. Unlike the other two steps that we've used so far, the salting out and the ion exchange chromatography, where we really thought hard about the charge of our samples, either the net charge was 0 to facilitate salting out, or the net charge was was positive or negative with regard to the isoelectric point, in order to stick to the solid phase of our anion exchange or our cation exchange column. In this case, we're separating on the basis of size, so not charge. And what we're looking at in this schematic is another column. You recognize this now. But in this column, we can see the solid phase pretty clearly because these beads tend to be large compared to the tiny plastic beads that are modified with charged chemical groups for ion exchange chromatography. And that's what we're looking at all the way to the left here, is a blow up of one of those solid phase resin beads. It's called a gel bead or gel matrix. And when you zoom in on the gel bead, you see it has passageways, those darker channels through the gel bead actually allow small particles to go in, but they exclude larger molecules. So in this case, the larger molecule is blue and the smaller molecule is red. And so the red particles are going to be, they're going to be trapped inside the bead until they find their way through and then exit the bead. And then they're trapped in the next bead and eventually find their way through to the next bead, and so on and so on. And for that reason, gel filtration chromatography separates based on charge by impairing the mobility of the smaller molecules, the red molecules, while excluding the larger molecules, the blue molecules, so that they actually fall through around the beads and travel with the mobile phase. Up above is the tank of buffer, the solvent, and in this case we don't need to set up a gradient because, again, we're not using salt to compete off our protein. We just are using time and volume. So by separating our mixture based on size and collecting fractions in test tubes, as shown here, the larger particles, our protein is the blue in this case, will elute first, and eventually those smaller particles, our contaminating protein in red, which have moved along the solid phase of the matrix, are actually going to elute later. Okay, so when we look at the solute, in this case, you could still use absorbance on the x-axis, and then the volume of the eluted fractions, or you could have fraction number on the x-axis, and you can see that there are two peaks. Again, they probably wouldn't be colored, so you would need to assay the fractions to find your protein and also the quantity of your protein. Okay, so gel filtration chromatography separates on the basis of size, with the large molecules coming out first and the smaller molecules coming out after that. Affinity chromatography also uses a solid phase and a mobile phase, but the difference now is that we're not using size or charge. We're actually taking advantage of binding specificity. So in this case, our protein binds to another molecule, and all proteins function by binding to something. If that molecule is easy and inexpensive to obtain, we can use that molecule or ligand and have it affixed to the solid phase, as shown here by these black dots. These are the ligands anchored to the solid phase. And our protein, which is the red protein in this case, very specifically binds to the black ligand. But none of the contaminating proteins, not the blue Pac-Man or the squarish green molecule, they don't have any affinity for the black ligand. And so they wash through with the mobile phase and are found in the earlier fractions. In order to release our protein from this matrix, this solid phase, you could add free ligand. So you could add a free black ligand to the matrix, and it would move with the mobile phase and capture our red protein if it's in excess of the immobilized ligand on the solid phase. Now at this point I often get the question, but if it's already bound to the ligand on the solid phase, it's not available to be captured by the free ligand that you add to elute our protein. And what you have to keep in mind is something that we haven't really hit on yet, which is binding equilibrium. Proteins that bind other molecules are binding and releasing and binding and releasing. And so eventually, if there's an excess of free ligand, in that released step, the excess free ligand will win the competition for our red molecule, and it will move with the mobile phase, with the buffer and elute.